we need some other time for the explanation.
Uncle, send the number you see me. I'm interested on learning this model.
It's okay, no problem.
It's all right. It's all right. We will talk about it probably maybe after the class or something like that.
That's what I'm saying. Uncle Koyende Bello, send the number you
It's
see.
okay.
Again, class.
All right. Thank you. That's great.
Thanks for your time.
It's okay, no problem.
Yes, sir.
I'm also interested in the to understand the concept and the working, how the bank works too.
You will pay me, I'm the initiator of this project.
What I will do
all right.
I will try and get some material and maybe share it if it is allowed.
Okay.
And maybe share it on the via the WhatsApp if it is allowed. If not, then maybe I will try and send it to you individually.
For data management, don't do that, So
yes,
we have to be careful. So
if
I prefer verbally like this, so that in fact I cannot read books, but make it personal, so that it will be a kind of low key for data purpose.
Okay. It's okay.
It's
all right.
Yes, sir.
Thank you very much for that insight, Mr. Kainde. We really appreciate.
You see now, I know how to ask questions, even though I don't know how to read book.
All right, so we're all welcome to today's class. This is our lecture 6 in our lecture series since we have started probability theory and distributions. And so far so good. We have been on so many things. We have talked about the random variables. We define probability. We understand what it means when we say probability distribution theory. We explain that. We understand that in probability distributions there are 2 kinds. We have the discrete and the continuous. When we say discrete, we expect that people should think of a particular value, like a discrete value or an integer. And when we say continuous, we say that it's expected that one should think about a range of values. And so far so good. We have done a lot. We have see how we can understand some distributions, how they work, how we can characterize them, their differences, their properties, their mean, their PMF, their CDF, and so on and so forth. So today we will continue in that regard. But we had one assignment last week where we stopped and we say that when we come today, everyone will present his or her own, maybe one distribution each, and then will give us some more insights based on the research and the understanding of the research, and then of the distributions. And then we say that if possible we can shed more light and even ask questions on gray areas to understand better and to deepen our knowledge and understanding of how these distributions work and how they are applied. So we're all welcome to today's class. So I don't know whether are we all ready for the assignment? With the assignment.
Sorry. The assignment, I don't know how to put it in that overleaf of a thing. I've done mine. It's in my book here. So if you want me to scan it to you, because it's more of a theoretical thing, just looking into the PDF, the probability density function, the cumulative, and other properties related to that distribution. That's all I did.
Okay, but you should have used PowerPoint now if the overly flat text is not working. Maybe you should have used PowerPoint.
Okay, PowerPoint. Okay.
Yeah, so that you can project, because you can't project what you have written.
Yes, I was so worried, but I said if the words come to us, you can see I should scan it. I can't project it. Yes, I could have used PowerPoint. It didn't really occur to me like that.
Yeah, you will still explain to us what you have found out. But so far so good. Let's hear from others, especially those who have it, who can present, who have it and they can.
All right, thank you.
Let's start with I think Mustafa should be next. Mr. Mustafa, are you there?
Good evening, sir.
Yeah, evening, sir. You're welcome, sir.
No, I'm sorry. Sorry, sir. I'm so sorry for I've not been here. I've not been attending the class since last week.
Okay.
So my phone was have some small faulties. So
Okay.
I just
So
collected just now. I'm just, I just came back home, so I joined the class. I don't know about the assignment.
wow, interesting. Okay. Mr. Kainde, are you there?
My apology. I don't know if you called me earlier on. I have to answer my ED, so I'm just back now.
Okay. All right.
I think I met discussion on the assignment.
Yes.
I've started it. I've not finished.
Okay.
I have to. My apology because there were times that even though I will attend, but between here and out of the office. But I have to like go and re-download all the materials from the site early this morning, and
Okay.
I found
So far so
there are.
good. Which one have you done?
Let me open. I'm opening them one after the other because I know there is one on the husband and is it a husband and wife also? I'm
Okay.
trying to.
Yeah, we have discussed on those ones. We are actually interested in the one we gave last week.
Okay, last week.
Yes. About
Okay,
about the Pareto distribution, the Cauchy, the logistic, the beta and the beta
okay,
distribution.
okay. I think that is the third assignment. Okay, I'm reading it. Okay, no, I've not started that. So
Okay.
can I just drop the other one and just do this one?
Okay, you are done with those other ones?
No, I'm wrapping up the first one.
Okay. All right. Based on the calendar, I don't know whether we are all aware. We're supposed to have mid semester exams next week.
Okay,
Yeah, there's going to be mid semester exams next week. So
okay. I don't know. I have a suggestion around this.
okay.
If we are going to have a semester exam, uh,
Yes.
is it not possible to give us like a week free period so that uh, for us we can also use that period to for catch up, to go back to the material, go through it, and be better prepared so that it will not just be that from the lecture we are just jumping straight into the exam.
Okay. The mid semester exams is more like tests and assessments, which comprise part of the grading. There's going to be the final exams.
Yes, I know. Um, but that is what I'm thinking. It might not be the same view from others.
Okay.
I'm sorry if I'm being selfish, maybe because I'm looking at the constraint that I have at my end. So that's why I'm
Yes.
actually talking like that. I'm very sorry about that.
Okay. It's all right. I will put that into consideration. I will ask. I will talk to. I will talk, and then I'll present it forward. Then whatever comes, maybe the response will be sent on the WhatsApp.
Yeah, Mr. Coinde, you are not the only one in this view because the fact that everybody's working, in fact, as you can see, the class hardly get to its maximum number. So if we are being sincere, because many people are being challenged as a result of a time constraint,
Okay.
so it's good to give. It's either you turn this midterm exam to midterm assignments
Okay.
and with submission. Therefore, in the next coming exam, you give us a week to prepare. Like he said, everybody is working. In fact,
Okay.
as a person goes beyond. I have to cater for children. I have to work. I have to do everything. I'm not the only one. But I'm just trying to let Mr. Coin there understand that we are
Yeah.
almost all in this shoe of
Together.
no time at all.
Yeah. Yeah. I understand. The assignments are also part of the mid semester exams. I don't know whether you understand. The assignments are all part because they are all part. It's just that there may be some additional questions, maybe on the day on our in our next class. In our next class, instead of having a class, we will have a link shared, and people will just go like a Google test or a Google. So I don't know whether we have written such exams before or tests or exams before.
No, what he's saying is that we need time to prepare. You didn't put that time to prepare for this exam. That's what we are
Okay,
saying here.
okay.
Like this week now, maybe it could have been, oh, okay, this is the exam. We're going to cover social topic. Any question related to that topic that you don't understand, then we discuss it in this class, believing that
Okay.
next week is our test. That's
All
what we
right.
are saying.
Okay.
Because of
Okay.
the condition attached to, or what's it called? The students involved,
Yes.
the parties here, they are not just full-time education. That's
Yeah.
what he's
Exactly.
trying to present. Yes.
Exactly. Exactly. All right. It's noted. It's noted. It's noted.
Yeah.
I'll see what can be done about that, and then we'll
Yeah.
get feedback as soon
Okay.
as possible.
Yeah. That's just where I see it. Thank you. I think I've spoken it out well by Mr. Kondi, because it's everybody anyway.
It's all right.
Yeah,
So,
yes. Thank you very much.
Yes, sir.
Thanks.
Yes, sir.
all right. It's cool. It's cool. So, in that case, let's continue with today's class. So, Mrs. Ebun, do you have anything to share based on the assignment that you have done?
I mentioned earlier on that, yeah, I made attempt. I mean, it's more of theoretical issue. So
Okay.
it's just
Yeah.
going
Just
through the
yeah. Go ahead.
distribution.
Go ahead. Go ahead.
Yeah,
Just give us some general and overall
understanding. Okay.
understanding and something you think that is very
That is
useful that you have
important.
discovered.
Okay.
Yes, that you have discovered.
Okay.
I want to share.
So trying to look at for Koshi and logistics, I couldn't get anything together. So I separated it by saying, let me look for each one, the Koshi distribution and then the logistic distribution differently.
Okay. All right.
So, but what I found out was that um apart from the I won't kind of there's PDF, but with Koshi there's a lot of properties. But what's it called? This Koshi distribution has two parameters: the
Okay.
location parameters and the scale parameters.
Scale parameter.
Yeah.
Okay.
So if you, I mean, when I read through it, I remember the class we had in the seminar, Ashura seminar, where we tried to do the hypothesis issue, where we're looking for the location and the scale.
Okay.
So, but though I don't think Koshi was added to the distribution analyze. So
Okay.
I could pick it from there. So, but there is a special case where if T, which is one of the parameter, the local parameter is equal to 0, and the scale parameter S is equal to 1, then that comes to the standard Cauchy distribution.
Okay.
So that, I mean, that's, like I said, is just what is in the note I'm reading out anyway. And
All right.
I believe Cauchy is very good for actuarial because it has a lot of property. In it, there is a function you can use for hazard.
Okay.
There's a function, you understand, hazard function. So talking
Yes.
about,
Yes.
yeah. So there's a function for survivor.
Yes.
There's a function for inverse survivor as well. So it's
Okay.
really good for, I think, life insurance, in my own
Okay.
understanding. Though I can't apply it now, but I believe with my understanding area there now, it means that it's very good for the study of what's it called, or what I've
Life.
said. Yeah.
All right. All right. All right.
Then
That's great.
yeah. So then talking about then they mentioned that the Cauchy distribution is important as an example of a pathological case, which asks me, I don't really have good understanding.
Pathological. That's disease.
Aha, you see what I mean? So I realized that this distribution would be very good for life insurance, all those kind of thing. And then what's it called? Again, they said that if I read this, please, when studying hypothesis tests that assume normality, and the normality, what's it called? See how the test perform on data from a Cauchy distribution is a good indicator of how sensitive the tests are to heavy tail departure from normality. So when you are performing what's it called, your hypothesis, and it departs from the heavy tail normality, then it shows that it goes in the line of Cauchy distribution. So that's just one thing I've seen in that. But coming to what's it called then?
Logistic.
It's, yeah, logistic. So okay, no, there's something I wanted to. That's why I said the Cauchy is very, very funny. The mean and standard deviation is undefined. So when I
Okay.
tried, yeah, it's undefined. So and I tried to look at and then the mean and mode is the location parameter T. So it's always, so the mean and the mode is it. So it shows that when there's no mean and when there's no mode and media, then it turns to standard Cauchy, because if it's zero, then it means that it's not existent, and the skewness is zero as well.
Okay.
So I tried to understand what they mean by undefined, but I'm trying to look at it. I didn't really
Yeah,
get it.
undefined means it cannot be determined. Just like when you say
To
anything
infinity.
divided by zero. For instance, if you carry a value, you say divide by zero, you know it's undefined.
Yeah, that's it.
So that's what they are trying to tell you, that is
Yeah.
you can't. It's non-deterministic. You can't determine it.
So that's just it. Then with the logistic, there's nothing much, even though it's one of the continuous distribution function.
Yeah.
Or the parameter, it takes the parameter between 0 and infinity. It has two parameters, mu and s, which are done. So the mean and the s, which I believe the s is the what's it called, scale parameter. So going by all the formulas, that's just the only thing. So rather than having T like Cauchy is
Cauchy.
having mean as is one of the parameter. That's the only difference I see. And they said it has been used in the physical science, sport modeling, and recently in finance. So
Okay.
such as the logistic regression.
Regression.
So
Yeah,
that
exactly.
I don't know.
Exactly.
Don't know anything.
Okay,
I
you've not
tried
heard of
to look
logistic
into.
regression before, right?
Yeah, I've heard, but I couldn't comprehend much about it. But
Okay.
but I knew that there's what they call logistic regression.
Regression. Okay. All right.
And then the Pareto distribution is a bit common, even though we even use it as 80-20 rules of Pareto.
Yeah.
So yeah, so that's just them. It has the is continuous with the what's it called, a, which is the initial value between 0 and infinity, and the distribution, they give the distribution is a formula, but the special case is that when a is equal to 1, when it starts from 1 rather than 0, then that gives us a standard Pareto distribution. That's
Okay.
just like I said, I'm reading out anyway. But
Yeah, you actually did well.
yeah,
I'm impressed. But sometimes the important thing is that we should be able to understand the function of the scale and the parameters used, whether it is scale or shape or location parameter.
yeah.
Because usually, depending on the material you are consulting,
Mm-hmm.
you may get different alphabets or Greek alphabets
Yes, that's
used.
why I didn't want to say a particular one, because they just gave G here, but it can be K, it can be anything in
Yeah,
any other place
it
book.
can
Yeah,
even be those Greek alphabet like
yes,
lambda, sigma, and the rest of them. Yeah, the
so,
important thing, or what one should do, is that anytime you are writing them, you must specify that where this is the scale parameter, where this is the location
yes,
parameter,
yes,
and where this
yes,
is the shape
yes,
parameter, and so
yes.
on and so forth.
Okay,
Yeah, so
okay.
any
So A is a shape parameter for Pareto, and in this example, and B is the scale parameter. Yeah.
okay, it will have been great if you were
If I
projecting
could
on.
present it, yes. And
Yes,
I've
yes,
told
yes,
you the
yes.
problem I have is having to type. I went to that, I even did it this morning before I start doing my daily activities. I said, let me quickly use 1 hour. But when
Okay.
I went there, I went there, the overleaf, I typed, and to be candid, when I went to the Z compiler, it didn't give me
Yes.
what I typed, and I
Oh,
closed my
okay,
laptop and I ran for the
okay.
daily activities.
Well, next time you can use you are familiar with PowerPoint, right?
Yes, I pray. Is that for those formulas that is the major thing?
Okay. All
Mm-hmm.
right. But
Yeah.
if there's a way you can snipe it, you can use the sniping tool. Do you know the sniping tool?
If I
The
know you,
snip
I
the
would have
snipping
done
tool.
it.
All right. It
No.
helps you to just screenshot maybe whatever maybe the formula, and then you can now paste it as a picture.
You see what I mean? I could have done it that we've had known. Yeah, okay. Maybe if we have time, you can, because of class, you can put me through properly. Because I've done it, I put it in my notes here, but I couldn't uh put it better because of all the formulas involved. So I will screenshot, then take it down to where I wanted to paste it.
Yeah, that's okay.
Is that what you're saying?
Yeah, you can do it that way. You can save it, and then when you're using the PowerPoint, you can copy it as picture and put it.
Okay, okay, I got it now. Okay, I'll try. I'll try, but if I fail, then I'll let you know. Thank you very much.
But
So that's
you're
just
welcome.
all about it.
All right, you have done well. If we're in a physical class, we'll have clap for you. But
Everybody is clapping. I can see their hands.
okay, they answer me. All right,
You
all
see,
right, all
people
right,
are clapping here now.
all right. So it's okay. That's cool. So I like what you did, because it shows that now you have much more knowledge and understanding of what we have been talking about so far. I'll continue to this class. I'll present my own side of the findings, and then the explanation on some of those distributions, so that I will shed more light on the remaining distributions that we're talking about. Because so far so good. These distributions that are left, when we are done with them, we are done with the commonly used distributions in the discrete and in the common continuous distribution. So in our next class, it will be uh, another thing entirely. So it's like today we're wrapping up everything on distributions, discrete and continuous distribution. The others might be maybe talking about some bivariate distributions, and then probably multivariate distribution, and then moment generating functions, and others. But we are going to take some time to summarize and to explain more, and to ask plenty questions concerning anything distribution, so that once we have passed distribution, then we know that we have less to worry about. So permit me to present my screen now, so that we'll start from there. I don't know whether you can all see my screen.
Yes, yes.
All right, all right, that's fine. So uh, today on probability distribution theory and distribution, we will be talking about these are table of contents for today. We have the introduction and recap. We have today's lesson. We have Pareto distribution. We have Cauchy distribution. We have logistic distribution. We have the beta distribution, and then we have summary and conclusion. Feel free to ask questions anywhere and any point we have reached, and you need clarifications, or you want to contribute, or you have some observations. Please feel free to uh, raise up your hand and then ask questions and let me know. All right, introduction. In our last previous classes, we talk about the continuous probability distributions. We say we know that we have the discrete probability distributions, and then the continuous probability distributions. And we have talked about the discrete, which includes the binomial, the Bernoulli, the discrete uniform distribution, and so on and so forth, and the geometric distribution, and the others. And then last week we talked about the continuous probability distributions, and especially we talked about the standard univariate continuous distributions. I remember I did say that when we say univariate, we are saying that it has one, we are considering one variable. And we say that there is also the bivariate and the multivariate continuous probability distributions, which we are going to look at after this class, in our subsequent classes. I would say part of the commonly used standard univariate continuous distributions include the uniform distribution, we have the normal distribution, we have the student's t distribution, we have the chi-square distribution, we have the f distribution, we have the exponential distribution, and then the gamma distributions. In our last class, we talked about the PDF, the CDF, the mean, the variance, some properties of the uniform distributions.
You are
I
not
did
audible
say that we
again.
should remember.
You are not audible at all.
Okay, I was not audible. Oh, I think it, hello, are you getting me now?
Yes, just now.
All right. So today we'll talk about the Pareto distribution, the Cauchy distribution, the logistic distribution, and the beta distribution. I believe that based on our last assignment, we already have idea and some understanding about all these distributions. So we'll add today we aim to add more on some other ideas or distribution that we have missed when we are researching on these distributions. So we'll start with the Pareto. Now, in our last class, we showed that we showed how the log normal distribution was used to model the amounts of insurance claims. And we gave some examples. Now, we can also use the Pareto distribution to model certain insurance loss claims. Certain, mark the word certain, insurance loss amounts. Now, what we are seeing here is the plot of the PDF of the Pareto distribution. And here, if we look properly, we see that based on the density side, we have 0, 0.5, 1, 1.5, and so on upward. And then under, that's the horizontal side, we have the loss amount in hundreds of dollars. And we see that we have 0, 2, 4, 6, 8, and 10, which means that what this graph is saying is that when we say the loss amount in hundreds of dollars, we are saying that this 0 here is $100, this 2 here is $200, this 4 here is $400, $600, $800, and $1,000 or $1,000. Now, if we look at our curve, we see where the curve is following. It seems as if the curve is at 3, right? The curve seems to be at 3.
Yes,
Yeah,
yes.
so which means we're having
Sorry, I've been
$300.
raising my hand for a clarity.
Okay, go ahead.
Yeah. This distribution, this new one you want to present, they are
Yes.
multivariants. Is that
No, they are still univariate.
okay? So why are they having two what do you call it?
2 parameters.
Yes.
Okay. All right, I understand your question, but
Yeah.
I don't have a clear answer to it now.
Okay, no problem. Just
Yeah,
kind of
yes. I don't have a clear answer to it.
Can we say, I don't know, just again, can we say there is a dependent and independent variable, and the independent variable is just one?
Okay.
Could be.
That's another side to it, but I can't confirm now so that I will not come and say confirm me wrong something, and then
Okay.
after getting my some info,
Okay.
down. Yeah, but I'll write down the question in my memory, and
Okay.
I'll write it down. Then when in our next class, I'll be sure to talk about it.
All right.
All right. So, so looking at the Pareto, like I've been explaining, so we're trying to understand how this works practically. I don't know whether you understand what I'm trying to say.
Yeah.
Yes, so we're trying to understand how this works practically, especially as we are talking about the claim amounts, how we can model claim amounts using the Pareto. So we see down here we have the loss amount in hundreds of dollars, and then we see that our graph here is at 3. From the top, we see that it's at 3, which gives it which makes it $300. So though because it's not full, we don't know where it stops because I think the graph continues up. So, but let's continue. All right. So note that the distribution starts at x equals 3. That's $300, right? Start at x equals 3, right? That's
Yes,
$300.
yes, yes.
Now, this means that this insurance policy has a deductible of $300. It means that it has a deductible of $300. What do we mean by that? We mean that the insurance company only pays the loss amount. It pays the loss amount minus $300, which means that claims for $300 or less are not filed. So if you insure with this particular maybe this particular policy, it means that if your claim, whatever you are trying to claim, if it is $300 and below, you can't file it. That's one peculiar thing I think about the Pareto distributions. So if you're in a situation whereby if your claim is up to $300 or less, you can't file it, then I think the Pareto distribution is appropriate. So here, thus claims for $300 or less are not filed, and the only losses for interest are those for more than $300. So if you have more than $300, you can file your claim. But if you don't have, if your loss is not up to $300, you cannot file any claim. Now, this is the density function for the Pareto distribution. Now, there are diverse ways these distributions can be written down depending on how you understand your mathematical simplification and what you want to use it for at that moment. If we notice, if you look at the this particular Pareto density function or probability mass function, it has two parameters, which is alpha and beta. The alpha is the scale shape parameter, while the beta is the scale parameter, as we have seen from the graph. Here we see that the beta is the scale. The beta is the one at the loss amount. So it scales, it gives it scales the graph or the distribution or the behavior of the data. So here we see that we have our f of small f of x, which is the PDF. By the way, the difference between, if you want to differentiate between a CDF and a PDF, is to look at the function, that's the f of x. If it is small f of x, then it is PDF. If it is capital F of x, then it is CDF, right? I'm sure
Yes,
this is basic.
yes.
Yes, that was supposed to know. Now, for the PDF here, we see that we have alpha all over beta into bracket beta over x, all raised to the power of alpha plus 1. So this is the method that this particular text that I used wrote their PDF. Hope you're observing. Now, if we go further, you see that this particular text is writing the PDF in a different format, but it's the same thing.
This is the one I have. Was
This is the
kind
one
of
you have, right?
yeah.
Yeah, but it's the same with this one. They're exactly the same thing.
Yeah, yeah. If
Yes.
it's
Now,
properly expanded, yes.
yeah. Now, if you let's just do
It's
small
expanded.
expansion.
Yeah, I know. I understand. I know.
Okay. All
Yeah,
right. All
I
right.
got it. Yeah.
Yeah. What about the others? I'm sure we agree with that too. That's the same thing.
Yes, sir, we agree.
All right. So here we see that our alpha is greater than 2, which is 2.5. We mentioned there that is 2.5, and then our beta lies between 0 and x. So here we are saying that beta is greater than or equal to no, beta is less than or equal to x, whereas beta is greater than 0. So we can see it here from the graph here. It's greater than 0, which means it can never pass down. It can only be greater than 0. It can only lie on. I believe you understand what we're talking about. It can only go straight, but it can never be less than this 0 here if we're considering the scale. Yeah. All right. So with that, the Pareto. So this example we give up, we say that alpha is equal to 2.5 and beta equal to 3. And the 3 there is $300. So we just have to convert it for easy calculation and simplification. So if you are maybe doing your claims, you can multiply it by in hundreds. Whatever you get, probability you get, you can multiply to have the value in amount in amount to make it clearer for use. Now the Pareto density in the previous figure has alpha equals to 2.5 and beta equals to 3. The density curve is so. We cannot get the density curve if we substitute the values for alpha and beta here. So alpha here we have 2.5 over beta 3 into bracket 3 over x. X here because we've not yet asked the question. We've not yet asked which claim we're looking for. We've not yet asked. I don't know whether we understand. If we say, okay, we're looking for a claim above a particular price, that's where our x comes into play. And don't forget, we see that for the Pareto distribution, x must be greater than or equal to 300 for that claim to be able to file. And that's why we have it here, x greater than or equal to 3. All right, so this will give us the density curve, this value here. All right, so the PDF, you can write it this way, just like I was saying earlier on. The Pareto distribution can be written here. It has two parameters, the alpha and the beta. And then here we have the beta, the x is greater than or equal to beta. So the claim must be greater than or equal to beta. The claim filing, the probability of that claim, that loss must be greater than or equal to beta. Where alpha is the shape parameter and beta is the scale parameter. And we know the function of the shape and the scale parameter. Probably as time goes, I don't know, maybe there's a module that will give us more explanation on the function of the shape parameter and the beta, the shape parameter and the scale parameter. But let's just know that the shape parameter controls the shape. That's in layman understanding, it controls the shape, while the scale parameter scales the distribution. So here we have the cumulative distribution or the Pareto distribution. Now we notice that we have 1 minus beta all over x raised to the power of alpha, and then here too x is greater than or equal to beta. That's the random variable that the value that the random variable can take must always be greater or equal to beta. Yeah. So like I've said earlier on that alpha is the scale parameter and then beta is the alpha is the shape parameter and then beta is the scale parameter. So here we have 1 minus. Now someone might ask that how can we differentiate between when to use a PDF and when to also use a CDF? Say you have a calculation. Even though I've explained that in our previous class, we say that the PDF gives the probability of that exact value, while the CDF gives the cumulative of that particular value or less. I don't know, is that understood?
No, sir, please repeat that one.
Okay, I say the PDF gives the probability of an exact value that we're looking for. That's PDF or PMF, whichever way you call it, or the density function. Then the CDF, the cumulative distribution function, gives that particular the probability of that particular value or less or other values. So it's like you are summing from 0 to that particular value that you're looking for.
Yes, that's why it's called cumulative.
That's why it's called cumulative. Yeah. Or should I give a simple example?
I'm clear. I didn't just say it properly. That was what I said.
All right.
Sorry, sir. Please, I need an example of this cumulative distribution function.
Okay. Let's say you toss a die six. You know, the sample space of a die. Let's use a simple die is 6, right?
Yes, sir.
It's either you get a 1 or a 2 or a 3 continually up to 6. And the probability of getting 1 is 1 over 6. The probability of getting 2 is 1 over 6. The probability of getting 3, 1 over 6. I'm sure you are clear with that one now.
Yes, I'm clear.
Yeah, even the probability of getting a 6 is also 1 over 6.
Yes.
Now, if you are looking, if we're talking about PDF, then they will say what is the probability of getting a 1? You know, it's already 1 all over 6,
1
right?
over 6, yes.
Now, but if you're looking for a CDF, for instance, you will say, okay, probability of getting X is less than or equal to 3, for instance.
Yes.
So,
Okay.
which means you will now say you are summing probability of, you know, if it is less than or equal to 3, which means you are looking for the probability that the die will show 1 plus the probability that the die will show 2 plus the probability that the die will show 3.
Yes.
Yeah, so which is cumulative.
Okay, I understand. I understand.
Yeah,
You
so
have to,
you
it's
now
like
you
you
now
sum
add one
the
of
sum the all of
you sum the
sum
whole probabilities till that part, and that is why
okay.
you know total probability is equal to 1,
Yes.
and that is why most times you see like this of Pareto. If you are looking for a particular distance, you see they say 1 minus. You understand?
Yes,
That's
sir.
if you are looking for the probability to be greater than, and so on and so forth.
Yes, I understand.
All right. So let's look at this example 1. Even though here we are seeing 8.28, but it's example 1 for today's class. At the Pareto random variable in example 8.27, that one that we use, that we discovered that we say that the beta is $300 while the alpha is 2.5. Remember? Now, that's the example we're talking about. It had alpha equals to 2.5 and beta equals to 3. The cumulative distribution function is, so we have it here, f of x is equal to 1 minus 3 all over x all raised to the power of 2.5. Gotten from our formula here. 1 minus 3 all over x all raised to the power of 2.5 for x greater than or equal to 3. Now, if the random variable x represents a loss amount, find the probability that a loss is a between 400 and 600. So we see we're using cumulative. Since it's not a specific value we're looking for, but we're looking for a range. So it's between $400 and $600. B, find the probability that the loss is greater than $1,000. So this is the solution. For A, we're looking for the probability that is between, remember we use 3 for $300, and we use the same thing here. 4 for $400 and 6 for $600. So here we're looking for the probability that the random variable lies between $400 and $600 here. So, so x is greater than or equal to 4 and x is less than or equal to 6. So here we are looking for the probability that is between this range 400 and 600. So we'll use this formula for here our x in the first place will be 4, then our x in the second place will be 6. So we have f of 6 minus f of 4, which is equal to 3 over 4 raised to the power of 2.5 minus 3 over 6 raised to the power of 2.5, which gives us 0.3104. Now notice that we did not use 1. The reason why we did not use 1 is because we're not looking for greater than, but we're looking for between. Is that clear? Between 400 and 600. That's why we did not use 1 minus. Now, but now that we're looking for greater than for B, we discover that we have probability of x greater than 10 is equal to the sample space of 10, which is equal to 1 minus f of 10. So using our formula, we have 3 all over 10 raised to the power of 2.5, which gives us 0.0493. Right. The mean of the Pareto distribution is given by the quantity here. And let us not forget that we usually use mu for population mean and then small x bar for sample mean. So we're talking about the population mean for the Pareto is given by alpha times beta over alpha minus 1 for alpha for the shape parameter greater than 1. Then the variance of the Pareto distribution is given by sigma squared, which is equal to beta squared times alpha over alpha minus 1 squared close times alpha minus 2 for the values of alpha greater than 2. So with this restriction, it tells you that when the value of alpha is less than in the first one, the mean, if the value of alpha, sorry, here, it tells us that if the value of alpha is greater than 1, if the value of alpha is less than 1, sorry, is less than 1, then this will not hold. Because let's say it's less than 1, we can't have a negative value as a denominator. Because we can't have a negative claim, for instance. So it will not work. And then if the value of alpha is greater than 2, is less than 2, then it will not also not work in the variance here. So that's the meaning of this restriction, or this yes, this restriction, this condition. Now the next example, the Pareto random variable in the example we use had alpha equals to 2.5 and beta equals to 3. So we can easily obtain the mean and variance. So if we want to, from that example, from this example, if we want to get the mean of the probability that the loss is between 405 and 600, then when we use the value, when we use the formula for the mean here, we discover that we have the mean here to be 5, which is $500. It makes sense, right? And then the variance will give us 20. Are we together?
Yes,
Yes,
yes.
you are doing it.
Right. So far, so good. Is there any question? I take it as there's no question. All right, so let's go ahead. Now, example 3. So this is more or less like an application, more or less like an explanation. So suppose we are, and this example will give us how the Pareto distribution can be applied as well. Now, suppose we are analyzing insurance claims for a certain type of property damage. Say there's a property damage and we want to analyze the claims, the value of the claims for each individual policyholder. The Pareto distribution is often used to model the distribution of claim amounts, where larger claims are less frequent but have a significant impact on the overall loss. I believe that is well explanatory. Now, consider a property insurance company that insures homes against fire damage. The Pareto distribution can be used to model the distribution of fire damage claim amounts. Let's say the Pareto parameters are alpha equals to 2.5 and beta, which is the loss amount, equals to $1,000. Now, alpha is the shape parameter that controls the tail behavior of the distribution, which means that a higher alpha that indicates a heavier tail, meaning extreme values are more likely. I don't know where we understand that. It's more likely that we'll get extreme values. And then beta, scale parameter representing the minimum claim amount. In this example, the minimum claim amount is $1,000. It indicates that the smallest possible claim amount is $1,000. We remember from where we talk about the other one, the smallest claim amount will be 300, which means if any there's no claim amount that can be less than $1,000 in this example. Now, also the Pareto can be applied in liability insurance. Suppose we are considering a liability insurance company that provides coverage for personal injury claims. We can, there are wide varieties of things we can actually insure people on, especially now that there are some even emerging risks. So there are wide variety of things that an insurance company can cover. So for this example, let's say we are covering personal injury claims. The Pareto distribution can be applied to model the distribution of personal injury claims. Now, similar to the example we used above, the shape parameter alpha controls the tail behavior while the scale parameter represents the minimum claim amount. So, if you have an insurance policy that has room for a minimum claim amount, you know that the Pareto distribution is your sure plug for modeling such claim amount, such insurance. Now, in both examples, understanding the distribution of claim amounts is crucial for insurance companies to assess risks, to set premiums, and to manage their financial reserves effectively. In fact, that's the importance of risk analysis. It helps you to assess the risks. It helps you to set premiums. It also helps you to manage your financial reserve effectively. So once you calculate the probability and you see uh, how it lies, you can be able to do these functions with the information that you have. All
Sorry, I
right.
was raising my hand. I wanted
Okay.
to clear something. Um,
Okay.
the minimum claim amount, I understand via your explanation, but there's
Yes.
this kind of experience I have that if you want to, you something happen and the insurance company will tell you that your is it, I don't know the exact name they call it, but it's like okay, maybe if something happen to your car or house, so
Yes.
there's this amount that you have to pay towards it. Or is it the same thing as this minimum claim amount? Like maybe they've said, I don't know, they've insured you over the fact that okay, anything 100, anything you want to claim, you pay the £100. I'm just using that one as an example, or $100
Okay.
first before they is it the same thing?
No, I don't think it's the same thing.
Okay.
I don't think it's the same thing. I think this one means, let's say, you maybe you have a claim, you want to claim a particular amount, and the amount that you want to claim is not up to, for instance, $300.
Okay.
Then
Are
you
they not the
cannot.
one to set the amount on a claim? Maybe
Yeah, they are the one to set the amount.
okay.
Based on your policy, you already
My
know the kind
policy.
of
Okay,
damage.
okay,
You know the
okay.
kind of damage that
Yeah,
you
yeah,
want a
okay,
particular amount.
okay, okay,
So if
okay,
your damage is not up to that amount, then you can't come and say you want to lay claim.
okay. Through this policy. Okay, so
Yeah,
it's different from the one that okay, they'll say you will contribute a
pay.
certain amount towards the that's why I was a bit confused because it's almost the same thing like saying, okay, if it's maybe it's $200, then
Mm.
you have to be the I mean
Okay,
you
to
bring
top
the
it.
$100
Okay, to top it.
to top it here, something like that, but I don't know the name.
Okay.
Yeah.
Yeah. I think it makes sense. It
Uh-huh.
makes a bit sense, but I think that is dependent on the insurance company and how they want to
Okay.
run it. Mm. You get, there's no one size fits all for all
Yeah.
insurance companies.
Okay.
Yeah, it depends on the policy, and if you see the policy that is more uh, favorable for you,
Okay.
maybe you can subscribe to that.
Okay.
You get, yeah. So I think that's how it is.
Thank you.
All right. For the Cauchy distribution, which is also known as the Lorentz uh, distribution, is a continuous probability distribution named after Augustine Louis Cauchy. Uh, is there going to be any of us in this distribution class that will come out with a distribution that will name it after his name? Like maybe we'll have an Ebun distribution or something like that. That's by the way, sha. But most of these distributions are named after some mathematicians or some statisticians or some founders. So, for instance, this Cauchy distribution was named after Augustine Louis Cauchy. It is characterized by its probability density function and the CDF, which have unique properties, just like Mrs. Ibn was explaining earlier on. So, we can represent the PDF of the Cauchy distribution by this quantity. It has two um, parameters, as you can see, the x naught and the gamma there, the small letter gamma, where the x naught is the location parameter, just like Mrs. Ebon explained earlier on, and then the gamma is the scale parameter. So here the Cauchy has two parameters, the location and the scale parameter. The CDF of the Cauchy distribution is also given by the quantity here. We have capital F of x, which is equal to uh, 1 over 2 plus 1 over pi arc tan into bracket x minus x naught over gamma. It represents the probability that a random variable x is less than or equal to a given value. Now, these are some properties of the Cauchy distribution. We have mentioned we have stated the mathematical properties as the CDF and the PDF. There are others too, like the mean and the rest. But some observations that we can see from the Cauchy distribution is that the Cauchy distribution has heavy tails, which means that it has more probability in the tails compared to other distributions, like the normal distribution. There are more probability in the tails compared to other distributions. And when we say tails, we are talking about the extreme points. The extreme points means the tails. The tails. Secondly, it does not have a defined mean or variance. Remember when Mrs. Abel was explaining that the mean and variance are undefined. Yes. So the Cauchy distribution does not have a defined mean or variance. So which means we can, if we assume the Cauchy distribution, we can't determine the mean of our observations. Neither can we determine the variance of our observation because they are undefined. Also, the PDF and the CDF of the Cauchy are symmetric about the location parameter x naught, just like Ms. Abel was explaining earlier. So she has actually done her research very well, which is great. Thank you for that. The Cauchy distribution can be applied in various fields, which includes physics, finance, and also even actuarial science. And it is used to model phenomena with heavy tail distributions, just like we explained earlier on that one of the properties is that it has more probabilities in the tails. And I did say tails means the extreme values, the smaller extreme values, such as certain financial data and extreme events. Extreme events. Now, in summary, the Cauchy distribution is a unique continuous probability distribution with heavy tails and symmetric properties. It finds its applications in various fields due to its ability to model phenomena with extreme variation. So that's that for the Cauchy distribution. I believe that as time goes on, as we delve more and more into uh, this program, when we do more practicals, anytime we come across any of these distributions, we already have an idea of some of their properties, and when we're fitting them, when we're fitting data to this distribution, we will be able to ascertain or determine why a particular distribution fits a particular data and be able to give some reasons why that is that. Now, the next distribution, which we'll be talking about, is the logistic distribution. Now, the logistic distribution is a continuous probability distribution, just like we've said, and it is widely used in natural science and other fields. It has the PDF and the CDF, which have unique properties, just like every other distribution. And the logistic distribution is given by the PDF is given by the quantity here. As we can see, it has two parameters, the mu and the s. The mu stands for the location parameter, and the s stands for the scale parameter. The CDF also is given by this quantity here. We have f of x given mu and s, which equals, I believe we are familiar with all this representation, f of x given mu and s, which equals 1 over 1 plus e to the power of negative x minus mu all over s. It represents the probability that a random variable x is less than or equal to a given value. So let's take a scan at the PDF and also the CDF so that we'll be able to differentiate them. Now, some properties, other properties of the logistic distribution includes that the logistic distribution is symmetric about the location parameter mu, just like the Cauchy distribution, and just like Mrs. Abun has explained, earlier on in our findings, we also say that it has heavier tails compared to the normal distribution, which makes it suitable for modeling data with outliers. Most times outliers occur in data. We know what outliers is. Outliers are unprecedented extreme values that looks very unrealistic. Sometimes, if not properly analyzed, outliers can actually destabilize the calculation. So when you have data that have outliers, then the logistic distribution is more suitable than the normal distribution to model such data. Now, the logistic distribution is often used as a model for binary outcomes and in logistic regression. Now, logistic regression deals with binary outcomes, which is 0 and 1. 1 or 0 otherwise. 1 for yes, 0 for no. That's if one, if that particular this thing is, how do I even explain? If it is, if it is significant, or if it is, if we are using it, then for sure we can use it. But if it is we are not using, then 0. That's a logistic. That's a binary outcome. 1 or 0. 1 for success, 0 for failure. Just like we have explained earlier on. I don't know whether someone can remember from our previous classes. Yes. Applications. The logistic distribution finds applications in actuarial science for modeling insurance claims, survival times, and other variables. If yes, 1. If no, 0. And so on and so forth. Are we together?
Yes, yes,
Hello, are we together? All right.
yes.
So next on our list is the beta distribution. So far, so good. We have talked about the Pareto distribution, the Cauchy distribution, and the logistic distributions. We have seen their peculiarities, and we have seen some useful information and how they can actually characterize uh, some data. Now, just as a reminder, so that these things will not look too abstract, we said that random variables are outcomes from experiment or events. And for us to be able to characterize their behavior, we need probability distributions. So probability distribution help us to characterize the behavior of this data. So we have the discrete and we have the continuous. Now, the discrete helps us to determine probabilities of or behaviors of data that are like integers, or we're looking for a particular value, while continuous uh, help us to determine data in a range of values that is continuous, that is we're not that's not specific. So uh, anytime we are faced with some data, we can fit in this data to many distributions to see which of the distribution will best model that particular data. And once we have seen that, then we can now use that distribution to perform our calculations or our analysis. So basically, that's a summary of how this distribution works. So for the beta distribution, we let's look at the application first before we delve into the distribution more and more, and to understand some other examples. Now, the beta distribution is defined on the interval 0 and 1. This is a closed interval, 0, comma 1. And sorry about that. Thus, the beta distribution can be used to model random variables whose outcomes are percents, ranging from 0 to 100%. So those random variables that their outcomes are percentage. Maybe they say, okay, find the percentage of this or percentage of that. Then you can use the beta distribution more, and written in decimal form. It can be applied to study the percent of defective units in a manufacturing process, the percent of errors made in data entry, the percent of clients satisfied with their service, and similar variables. So generally, when we are considering outcomes, random outcomes that are in percentage, then we can use the beta distribution. Now, these particular people, Herzog et al., they use probability of the beta distribution to study errors in the recording of FHA mortgages. Now, there's some properties of the beta distribution includes the CDF, just like, and the PDF, just like every other distribution, continuous distribution. And here, the PDF is given by this quantity here. As we can see, the beta has two parameters, the alpha and the beta. The CDF is given by this quantity here, and the range is between 0 and 1. We say it's in a close interval, 0 and 1. And close interval, we can easily understand close interval. For those of us that are mathematically inclined, when we say close interval, we are saying less than or equal to and greater than or equal to. That's the meaning of close interval. Less than or equal to, which means it will start from 0 and then less than or is greater than or equal to 0, which means it will start from 0, then above 0, then continuously. Then it is less than or equal to 1, which means it stops at 1. So that's a closed interval. And that's what we mention here. We say is defined on the closed interval here, 0 and 1. And because we know once you divide percentages by 100, they cannot be less than 0 and they cannot be more than 1. So that's why we say that the beta distribution is more useful for random sorry about that, for random variables whose outcomes are in percentages. Let's take a moment to have a look at the PDF and then also the CDF. And then beta of alpha over beta, alpha comma beta, which we have here. One of this value here, beta b of alpha comma beta, is what we call the beta function, and is given by this integral of 0 to 1 t raised to the power of alpha minus 1 into bracket 1 minus t here, and with parameters alpha and beta. The mean here, that's the expectation of x. Remember, we say is the mean, or the beta distribution is alpha all over alpha plus beta, while the variance is alpha beta over alpha plus beta squared into bracket alpha plus beta plus 1 close bracket. All right, so let's use example 5 to get much more understanding of the beta distribution. Now, consider an insurance company that wants to model the probability distribution of the proportion of policyholders who file a
Sorry,
claim
before we
during
start
a
going
given.
to the example, I noticed in the beta
Yes.
formula, there's a particular T. Beta, no, yeah. There's a T. What's that one defined on? Because I can't see where it's been defined. I can only see S. And then,
Okay.
yeah,
The T they say is a beta function. Are you familiar with the beta function?
no, maybe.
Okay, I think if need be, maybe I will get more information about the beta function and then I'll
Okay.
bring it in the next class.
Okay, yeah,
Is there any?
I will, yeah, because I said beta function, not the distribution.
Yes.
Okay,
Not the distribution.
not the
There's what we call the
distribution.
beta function.
Okay,
There's what we call the gamma function. I don't know whether you have heard of that before.
okay, yeah,
There's what
okay,
we call the exponential function.
yeah, I got it
We
now.
use
So it's the function, not the
use
distribution. That was why I was
oh,
confused there.
Yeah,
Okay.
yes,
Then
not the distribution. There
again,
was a time we used the exponential function in the exponential distribution.
mm,
Remember? We even though we didn't
yeah,
emphasize, but we
yeah, yeah.
made mention of something like that. Yes,
Yes,
yes.
I can see the difference now. But there's another thing I've observed there. It's just an observation that of all
Okay.
the four, it's only beta that takes the form of integral, while others are kind of the cumulative is not integral, they are rather exponential. Is there anything that made a difference? You understand what I'm
Okay,
saying?
I understand. For you to let me just come from the foundation. For you to get the CDF, you
Yeah.
integrate the PDF.
Yes, I
I
know.
hope, I hope you know.
I
Ehen.
know.
Now, good. Yeah, good. Now, in while integrating the PDF for uh the beta
The
distribution,
Yeah.
you will reach a certain extent whereby you will get what we call a beta function.
Okay.
Do you
Okay.
understand? And
Yeah, I know.
you can't
In practical sense, I was only
okay.
trying to say that having look at we discussed four now.
Yes.
Others were using exponential and others, but that this one takes
Okay,
form of
yeah.
integral.
Yes, yes, yes.
So
Yes,
that
yes,
is
yes.
there anything I know that it's cumulative. You got to add it. I understand the math behind it, but there is anything in application or a better layman understanding of why this is taking the form of integral, why others are taking the form of exponential, or just a kind of just in terms of exponential. That's just what I'm saying.
Okay. Honestly, now I can't categorically give a
Okay,
difference
not a
why the
problem.
rest are using exponential or
Yeah.
what. Well, yeah, but I know that the reason why the beta case is this way is because it's using the others are using exponential function while this is using the beta function.
Okay, that's a
Yes,
very good point. Others are using exponential
exponential
function, while
function.
this is
Yeah.
using beta function. Yes.
In
Thank
fact,
you.
I think there are others that even use the gamma function self.
Okay, good.
Yes, like the
At least
gamma
it's what
distribution.
noted. Thank you.
Yeah, you're welcome. All right, so we have explained the mean and the variance. So let's see how we can apply it using practical applications. So, considering our example 5, we see that if we're considering an insurance company that wants to model the probability distribution of the proportion of policyholders who file a claim during a given year. So when we say proportion, it tells us that we can get it in percentages, right? So the company believes that the proportion of claimants follows a beta distributions with alpha equals to 3 and beta equals to 5. That's an assumption, a belief by the company. Now, let's solve it now. To find the probability of a certain proportion of policyholders filing a claim, we can use the beta distribution. Specifically, we want to find the probability that the proportion of claimants is 0.2 and 0.6. For instance, I don't know whether I understand. I want to find the proportion that the claimants is between 0.2 and 0.6. 0.2 in the sense that 20%, right? And 0.6, 60%. I believe that's clear. So we're interested in finding that the claimants lie between 20% and 60%. Now, first, we calculate the cumulative, the CDF of the beta distribution to find the probability that the proportion is less than or equal to 0.6. And then we subtract the probability that it is less than or equal to 0.2. All right. So uh, using the formula, we have that our parameters, we say first we are going to calculate the CDF. Remember, we say first we are going to, first we calculate, first here, we calculate the CDF of the beta distribution to find the probability that the proportion is less than or equal to 6 first. Then secondly, we will subtract the probability that it is less than or equal to 2. So using the CDF of the beta distribution, capital F of x here, alpha comma beta here, uh, we have now if we look at this CDF here, the integral is in front. Someone might ask, right?
Yes, yes, yes.
Yes. So it doesn't matter because this beta b into this beta function be into alpha over beta is a constant, so we can bring it out or take it in. Those of us who are mathematically inclined will understand. Actually, the integral affects the t here. This t here is like our right. So the beta that we brought in is a constant, so the integral will not affect it. Integrating a constant is a constant.
Yes, yes.
So where beta b into alpha over beta is the beta function. So using the given parameters alpha equals to 3 and beta equals to 5, we can compute the CDF as follows. So putting our parameter here first, remember what we said earlier, we're going to calculate the probability that the CDF at 0.6, then we can now subtract it from 1 at 0.2. That's what we say we're going to do. So here, putting 0.6, we have this value, and putting 0.2, we have this value. Then now, I think basically because the reason why we're having an integral here is because most times the simplification can only be done using a numerical software. Is maybe manually not possible to do.
To calculate, okay.
Yes, to calculate. So if you use the numerical software, it just use possible values and it knows what to do. It's very fast. It can assume thousands and millions of values until it converges. Remember numerical analysis? Those of us who did math, numerical analysis, until it converges. When it converges, then you have reached you have gotten what you're looking for as it converges. So now, if we use numerical softwares or numerical method of softwares, we will find that the CDF of the claim being 0.6 is approximately 0.768, and the CDF that is 0.2 is approximately 0.040. So we cannot do the subtraction. Remember what we say, the process of doing it. Therefore, the probability that the proportion of claimants is between 20% and 60%, is between 20% and 60%. How do we know that this 20% and this 60% is approximately B minus A? That's the greater value minus the smaller value, which is 60% minus 20%, because we're looking for the probability that the proportion of claimants is between these two percentages or these two proportions. So therefore, we have 0.728 or 72.8%. that if we convert it to 100. Now, is this example clear, or do we need
Yes.
more explanation?
Yeah, it's clear. To me, please.
Okay. How about others? Okay, I take it as it's clear, which means we can go on. So this example demonstrates how the beta distribution can be used in insurance to model the proportion, don't forget, the proportion of policyholders filing claims, and it allows insurers to assess risk and make informed decisions about pricing and coverage. In conclusion, we see that continuous distributions. Now, I'm concluding generally because so far so good. We have exhausted the common continuous distributions. I didn't say all, the common continuous distributions that are usually used, especially in actuarial science and some other fields. And we talk about the uniform distribution, the continuous uniform distribution, the normal distribution, the exponential distribution, the gamma distribution, the log normal distribution. We talk about today we talk about the Pareto distribution, the Cauchy, the logistic, the beta distribution, and every other univariate continuous probability distributions. So in summary, continuous distributions are actually mathematical abstractions because they assume the existence of every possible intermediate value between two numbers, like we have been explaining. That is, a continuous distribution assumes there is an infinite number of values between any 2 points in the distribution, and that is why it is continuous, because it assumes that there is an infinite, so it's not discrete, it's not specified. Yes, so it assumes that there is an infinite number of values between any 2 points in the distributions. And so we talk about the Pareto, the Cauchy, the logistic, and the beta. Some notable points is that the Pareto models claims, like the claim example we use, of a certain amount that if it is not up to that amount, then one cannot file a claim. We also look at that of Cauchy. One notable point is that the mean and the variance are non-deterministic, which means they are undefined. We look at that of the logistic distribution. One notable point about the logistic distribution is that it uses binary binary random variables, which I say is 0 and 1. And then we say it is mostly used in logistic regression. Then we talked about finally the beta distribution. And one notable point about the beta distribution is that it uses the beta function, and it concerns claims or values that are in percentages, so or in proportion. So I think with these few points, uh, we have some more understanding of the continuous probability distributions. So so far so good. Is there any question? Please, if there's question, I'm not possibly seeing your screen, whether you raise up your hand. You can just uh, start talking. I will understand. Is there any question? Is there contribution? Is there ideas to share? Is there points of concerns? Is there anything?
Okay. I want the last example of beta is lack of contribution, or let me say my assumption, thinking loud. The last example of beta where you mentioned, if you can go there, yeah.
Yeah.
So with this one now, with this example,
Yes.
where the probability of proportion of claimants is between between 20% and 60% is 72.8. So one can say
Yes.
that because the probability is high,
Yes.
we will be expecting that this particular policy, the pricing might be high, because it's like the probability is um very high, so people will be claiming on this particular policy, so they might want to uh price the policy a bit higher. I'm trying to relate it to real
Mm.
life example.
Yeah, yes. And it depends on that particular proportion. We know that okay, if those particular individuals that maybe we cannot set maybe their claims if they lie between the set proportion, that's
Mhm.
0.2 or 0.6, then we
Says,
cannot
yeah,
maybe set their own this in higher or lower depending. I don't know whether you understand,
yeah,
because we know that they will most likely come and claim.
yes,
Yeah,
because
so
it's
you might
high, 72.8.
yeah, because it's high, so you can decide to say okay, for this particular group of set of individuals or proportion of individuals, these rules and regulations should apply to them, or this policy should apply to them.
Okay. All right. That's just, I want to relate it to real life. Though it's already written here, but I want to relate it to real life.
Yeah, thank you for that.
Okay.
Yeah, any other? You have more?
No, for me, I'm okay.
Okay, all right, all right.
Yeah.
What about the rest? Mr. Mustafa, any question, contribution? Mr. Osawa, is Mr. Osawa online? How about Mr. Kainde?
Sorry, no question.
Okay, all right. So that's cool. That's cool. So, so far so good. We have talked about. Let me just give you a brief revision from. I think we've talked about random variable. We understand what a random variable is. Moment generating function. Probability distributions. Discrete probability distributions, continuous probability distribution. So randomly now, if I'm going to ask maybe a random question, okay, let me ask quickly. The uniform distribution, is it a discrete probability distribution or a continuous probability distribution? Yes, go ahead.
I will vote for continuous.
Okay. Mrs. Ebon, you agree with him?
I did not mute. Yeah, it's continuous.
Okay, all right, all right, all right. But we know that the uniform distribution is of two types, right?
Yeah, that's what I mentioned. I never knew that didn't on mute. That is discrete and continuous, is it?
Yes, we have the discrete uniform and then we
Yeah,
have the
and continuous one. Yeah.
continuous uniform. All right. Yeah. Then what about the geometric distribution?
Geometric distribution is discrete.
This are you sure?
I'm trying to think.
Okay.
Uh, yeah, I think it's discrete. That's the first one you taught us.
Okay.
It's,
You think or you are sure? Or it is
I'm sure. I'm sure that's what's the name again?
geometric.
I think that's where the moment generating function is. Yes, it's discrete.
Okay, let me throw this to Mr. Osao. What about the negative binomial? Is it continuous or discrete?
Oh my god. Negative binomial.
You are still thinking?
Is it me? I thought you said you are
It's
throwing it
not
to
here.
someone else. I don't
Okay, it's
want.
not here. Oh, all right, all
Um,
right, all right, all right. So
but I think
anyone
it
can
is discrete.
is discrete, right?
Yeah.
Yeah.
All right. That's nice. That's nice. So it means that we have a good knowledge of the distributions, which is cool, and that's the essence of learning them, so that we're able to differentiate them, know when to apply them, where to apply them, how to apply them, where they can function, which one they can fit better. But generally, all this knowledge is for our own personal understanding, so that we know how to use them better. But the software all the computer programs and
We take
software,
care
the
of it.
Python and yeah, they can take care of all these things. But we must understand how it works actually.
Yeah.
Yeah. So when
But
we
the
understand how it,
negative binomial distribution, or let me say geometric distribution, is related to negative binomial distribution.
yeah, exactly.
Okay.
They have we last time we gave the reasons what will make them special case of the others.
Hmm, I think that's the negative that I didn't
No.
get.
Is the
Yeah,
negative and
negative
the
one I
geometric.
didn't
Sorry,
get very well. Yeah.
it's not hypergeometric. It's negative, binomial, and geometric. They are the ones that are related. Not
Yeah, that's what I said. So it's that negative binomial that didn't get very where we I mean the geometry talks about all the trials before say success. So it's like
success. Yes.
you want a head and you've been training. So maybe the first
You are
head
interested in
shows at the
failures.
fifth at
The
the
number of
fifth
failures
yeah the fifth
before the
trial.
first success.
But this other one, it's a bit confusing that the number required. I got it a bit confused, but I will read more about it anyway.
It's all right. It's all right.
Yeah.
That's cool. That's cool. All right. So if there are no questions, thank you all for listening. But in addition to our discussion on the next week um, assessment,
Yeah.
uh, based on the concerns that were tabled today in the class, I'll
Yes.
forward it to the institute, and then
Yeah.
we will maybe we'll give some comprehensive direction. But be sure that all the assessment that were given, all the exercises that were given,
Hmm.
all the exercises that were given in all the classes, they form part of this semester exams.
Okay.
Yeah, they form a percentage. So they must be done. We have been giving graces all this while for
Yeah.
those who have not yet submitted their assignment.
So in your own class now, how many assignments we have? Just two or one?
Three. We have
You-
three.
Which one is the third one? Is it the one that I didn't type?
Yeah, the one that
Oh,
you did type.
in fact, that is I want to actually make a comment around this.
Okay.
Yes, was it yesterday when we were doing risk analysis?
Okay.
I made a comment on it. I missed some classes. There were some I just came in haphazardly, and I found out that there are assignments to be done. But if we have assignment, like for yours now,
Yes.
when I went to the drive,
Yes, sir.
I saw a folder called assignment, and all
Exa-
the assignments were there. That's how it should be for other courses.
Okay.
So
Yes.
that when
Yes.
we
Yes.
go there, we see all these assignments. But you go there, you don't see the assignment, and you get to class, we are hearing of submission of assignment. So I think
Okay.
you guys should also help us to organize these things so that it
Yes.
also makes life easier for us. Now you can hear what Ebony is even like. She didn't even know that there are three
Yeah.
assignments, right?
Yeah.
So
No, she
please.
she knows. She knows. It's just that she did not add up with.
Okay, okay. But at least I know that for your own, for this probability theory and
Yes.
distribution,
Yes.
I saw an assignment folder, and it was very, it really helped, because once I go into that folder, I could see
Yes.
all those assignments. I open them one after the other. I make the attempt. I think
Okay.
for
All right.
others, they also need to do the same thing. That
Okay.
is,
All right. I will relate it to. I will ensure that it's done that way. I will ensure that it's done that way. So, in addition to that, for today's class, I'm going to, if possible, I may add more of the assessment for the coming week. But let's just try and finish the three that we
Okay,
have on
this
ground.
one, this third one, I've already
Yes.
said it in class. It's just theoretical thing, just to type it. So
Yes. 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 You
could
need
can
to
that
still
be
type.
regarded as assignment?
Now that you have said, you actually how it's supposed to be, ba? You see now this contribution that you gave in class has his marks. Has his marks.
I hope.
Yes, has his marks.
So me and Mr. Coin, there we will pass when it comes to contribution.
But
at least for listening.
I
Yes,
mean,
for listening and
but
for me asking questions all the time.
yeah, but you still need to do it. You still need to do it though and submit.
Okay,
It's
so
okay.
this one that I've explained in class, I still need
Yeah,
to put it
yeah. You
in
still need to
writing and
you still
submit
need to
to you.
put it in writing and
So
submit.
you said
Yes.
I should use what to type it?
You can use PowerPoint. You can use Microsoft Word. How you can present it that is online.
Okay, PowerPoint or
Can be,
Microsoft.
yes, sent online.
Okay, so that once you click on it, you can see everything.
Yes, yes, yeah. Because you have submitted the other assignments now.
Yes, I have, but I can't
It's just
touch
for
it
you to
to
upload.
yeah.
When you go there, just fill in your details, the number, the designation of the assignment, and then you upload.
Hmm.
When you upload that, you go back
When I'm
again.
ready, I will call you again to show me how to submit.
Sorry, where
Okay.
are we uploading?
You
There's
see
a
now?
okay. There's a file for upload, but I think what I'll do is that I'll send my institutional mail so that it will just be uploaded there. Is that okay?
Okay,
Okay, it's okay.
Yeah, I think that's better, right?
yeah.
Okay.
Yeah, I'll send my
And then
institutional.
when it comes to this exam, you said we are going to use Google something. Why
Yes,
don't
Google
you
Forms,
Google what?
forms, or
Eh,
Google. Yes.
Why don't you run test and trial for people like me?
Okay.
So
What by test and trials? What do you mean?
what I mean is that maybe in class you do something on it and you ask us to do it so that we know that okay, we are all familiar to the platform and the usage. So if you just come to class, I might
Okay.
use like 10 or 15 minutes asking you where to click.
Okay.
You
Okay.
understand what
Okay.
I'm
Okay.
saying
I
now?
I understand what you're saying.
Yeah.
Maybe it's because you have not used it before, but it's
Yes.
clear. It's just like
Okay.
if it is objective, for instance, you will
Yeah.
see option A, option B, option C,
Okay,
option
it's
D.
like
You just need to click.
this our registered format.
Exactly. Yes, that's how
Okay,
it is.
okay, that's it.
There might be some places whereby you can just type the answer. Like
Okay, all right.
there's an explanation, you can just explain it there.
Okay, that's good then.
Then
I
you
thought
go to the next question. That's how it's done.
okay then.
It's not difficult.
Okay.
Yeah.
I
All right.
think
So thank you for joining the class. We will get more information before next week, but be sure that the assignment is a must before next class, and it forms part of the mid-semester continuous assessment.
okay.
Okay.
You can
And we
stop
should
recording now so that I can talk to my brother and finish the. We have 10 minutes more.
okay.
Okay.
The thing is that if I stop recording now, it will end the class.
Oh, okay.
Yes, yes,
That's
yes,
good.
yes. Mm.
Then I will talk. We'll make it again. What's your number? Huh?
Okay.
Since they say, I believe you. I can reach you on WhatsApp. Is it?
Yeah.
Okay. I'm trying to copy it now. Okay. Who it? Do it again, please. Who it to? Is it in the chat? Oh,
Yes. Yes.
okay, it's in the chat, Sarah. Okay, all right. Thank you. At least, so
Okay.
if the
If you
boys,
have finished copying, let me know so that I can end the call.
okay, just hold on. Oh, you are
Okay.
the one operating today. Oh, I
Mhm.
thought
Yeah,
it's
yes.
able. Yeah. Okay. So which of this is on the WhatsApp? And oh, they're both the same anyway. Okay, I'll try and put it down. Okay, I'll reach you, sir.
Okay, madam.
Is it now or later? Don't know how busy you are.
No, you can reach me. I'm still
Now.
in the
Okay.
office. Yeah.
Okay. Okay, sir.
Okay.
All right. Thank
Okay.
you, sir. Thank you, Mr.
All right.
Jacob.
Thank you all. Have
All
a
right.
great night and
Okay.
have a good night rest.
Okay. Bye.
Bye.
Yeah.